a 3 to 4-fold improvement in system efficiency over current thermoelectric radioisotope generators. Stirling generators. A Stirling radioisotope generator is a Stirling engine driven by the temperature difference produced by a radioisotope. A more efficient version, the advanced Stirling radioisotope generator, was under development by NASA, but was cancelled in 2013 due to large-scale cost overruns. Non-thermal conversion. Non-thermal converters extract energy from emitted radiation before it is degraded into heat. Unlike thermoelectric and thermionic converters, their output does not depend on the temperature difference. Non-thermal generators can be classified by the type of particle used and by the mechanism by which their energy is converted. Electrostatic conversion. Energy can be extracted from emitted charged particles when their charge builds up in a conductor, thus creating an electrostatic potential. Without a dissipation mode, the voltage can increase up to the energy of the radiated particles, which may range from several kilovolts for beta radiation up to megavolts, alpha radiation. The built-up electrostatic energy can be turned into usable electricity in one of the following ways. Direct charging generator. A direct charging generator consists of a capacitor charged by the current of charged particles from a radioactive layer deposited on one of the electrodes. Spacing can be either vacuum or dielectric. Negatively charged beta particles or positively charged alpha particles, positrons or fission fragments, may be utilized. Although this form of nuclear electric generator dates back to 1913, few applications have been found in the past for the extremely low currents and inconveniently high voltages provided by direct charging generators. Oscillator transformer systems are employed to reduce the voltages, then rectifiers are used to transform the AC power back to direct current. English physicist H.G.J. Moseley constructed the first of these. Moseley's apparatus consisted of a glass globe silvered on the inside with a radium emitter mounted on the tip of a wire at the center. The charged particles from the radium created a flow of electricity as they moved quickly from the radium to the inside surface of the sphere. As late as 1945, the Moseley model guided other efforts to build experimental batteries, generating electricity from the emissions of radioactive elements. Electromechanical conversion. Electromechanical atomic batteries use the buildup of charge between two plates to pull one bendable plate towards the other until the two plates touch, discharge, equalizing the electrostatic buildup, and spring back. The mechanical motion produced can be used to produce electricity through flexing of a piezoelectric material or through a linear generator. Milliwatts of power are produced in pulses depending on the charge rate, in some cases multiple times per second, 35 Hz. Radiovoltaic conversion. A radiovoltaic device converts the energy of ionizing radiation directly into electricity using a semiconductor junction, similar to the conversion of photons into electricity in a photovoltaic cell. Depending on the type of radiation targeted, these devices are called alpha-voltaic AV, beta-voltaic BV, beta-V, and/or gamma-voltaic GV, GUG&V. Beta-voltaics have traditionally received the most attention since low-energy beta emitters cause the least amount of radiative damage, thus allowing a longer operating life and less shielding. Interest in alpha-voltaic and more recently gamma-voltaic devices is driven by their potential higher efficiency. Alpha-voltaic conversion. Alpha-voltaic devices use a semiconductor junction to produce electrical energy from energetic alpha particles. Beta-voltaic conversion. Beta-voltaic devices use a semiconductor junction to produce electrical energy from energetic beta particles, electrons. A commonly used source is the hydrogen isotope tritium. Beta-voltaic devices are particularly well suited to low-power electrical applications where long life of the energy source is needed, such as implantable medical devices or military and space applications. The Chinese startup Betavolt claimed in January 2024 to have a miniature device in the pilot testing stage. It is allegedly generating 100 microwatts of power and a voltage of 3 volts, and has a lifetime of 50 years without any need for charging or maintenance. Betavolt claims it to be the